Um, we have seen greedy, we have seen divide and conquer as algorithmic paradigms, right? Kind of things in your toolbox that when you see, besides just looking at, oh, this looks like this problem, right? And we'll do a ton of those. It's like, oh, maybe I can do greedy and see what happens, right? And then when you get a problem, it's like, oh, maybe I can do greedy and see if it doesn't solve, right? If the solution doesn't solve. Divide and conquer, maybe I can do that. Maybe I can just brute force it, right? And see I compare with greedy. And now dynamic programming is like divide and conquer, but the sub-problems that you're solving are overlapping. So you end up solving the same sub-problem over and over again. So rather than solve it over and over again, you can either memorize it, which is store it in a different place, or build the table from the bottom up. It is used all over, right? So the thing that we looked at is the weighted interval scheduling problem. Find the maximum weight subset of mutually compatible jobs. The idea is sort the jobs in ascending order of finish times, and we can add a job to a subset if it is compatible with the previously chosen jobs, right? The greedy algorithm works if the weights are 1. It doesn't work if the weights aren't 1, right? This is an example, and we talked about this last time, right? Maybe? Nobody's complaining, so I'm assuming that is true. This new algorithm uses one more thing. Given a job J, given that we sort the jobs by finishing time, we define P of J as the largest index I less than J, such that job I is compatible with J. It may be more than one job that's not compatible, right? And so if we were to do this with divide and conquer, right? We are going to end up with basically two possibilities. One is, and we define OPT for optimal, right? Optimal of J as the value of the optimal solution to the problem consisting of requests 1 through J. So we're going to be building our solution that way. And OPT of N is going to be the actual solution to our problem. Does this notation make sense? Reasonable? So good. Cool. Now, how do we calculate OPT of N, right? Or how do we calculate OPT of J? There is basically two cases. One is, oh, we include J, right, in the optimal solution, right? So what is going to happen if we include J on the optimal solution? What's going to be the value of this solution? Well, it is however much weight J has, or job J has, plus the optimal solution up to P of J. Does that make sense?
What is P of J again?
P of J is the largest index that doesn't overlap.
Okay.
So basically, say I'm going to calculate 5, right? I'm going to say, okay, there's two possibilities. Either I include it, right? If I include 5, I'm gonna say, okay, the value of this solution is the weight of 5, right? Plus the weight up until here. In that case, there's nothing else. So it's just 5, right? Now, if I was doing, say, 7, right, on this slide, if I include 7, I will do the weight of 7 plus however was up until this time, right? That's what P of J tells you the jobs that are compatible, right? So 1, 2, and 3 are compatible with 7, right? So in order to calculate what's the optimal solution for the job that includes 7, it is the weight of 7 plus however much. What's the optimal solution for those 3 guys? Does that make sense? It's not time, it's jobs, right? Now, if I don't include 7, what's the value of that solution? The solution that doesn't include 7? Well, it's whatever it was optimal up to 6. Does that make sense? I don't gain anything by not adding 7. Does that idea make sense? Yes? No? Maybe? So for any given job, right? If I'm doing, let's do 8, right? Let's say that the weight, for simplicity, right? Let's assume that the weight of each job is 10 times the number. So the weight of 8 is 80, right? So, what is P of 8?
50.
Or it's 5, right? The lowest job that doesn't clash, right?
The job with the highest weight that doesn't clash?
No, with the highest number.
Highest number.
Because I sorted them all by finish time.
Okay.
So it is the job with the highest number that doesn't clash.
So we're outputting, or it's finding a weight value, but we're not using the weight value to find it.
We are. It's just, in order to calculate the optimal, right, we calculate 2 weight values. Mm-hmm. The one including the job and the one not including the job in the solution. Mm-hmm. And then we check which one gives me more weight.
Okay.
Right, that's what I'm trying to do. So for 8, right, P of 8 is 5, right? And so what I'm going to do is, if I include 8 in the solution, I'm going to have whatever I had up until 5, so OPT of 5 plus 80. If I don't include 8 on the solution, I'll get OPT of 7. Right? That's the weight. Does that idea make sense? So what I'm going to do is, at any given time, just compare those two and decide which one's better.
So if you include an 8, why you didn't take 7?
Because 7 is not compatible.
Oh,
if I include,
overlapping?
it's overlapping, yes. So I cannot include 7.
Okay.
Right? If I include 8, I cannot include 7, and I cannot include 6.
Okay. Because of overlap.
Because of the overlap.
Is the dynamic programming part of this? Is if you start at 1 and go down, you already have the optimal of each job you pass?
Basically, exactly. The dynamic programming, the bottom-up part, right? You could do it memoizing,
Yeah.
or you could do it bottom-up and start at here, right? And say, oh, for the first one, right? It's either 0 or adding the first one, right? So that's cool, but so that gives me this one, right? Now for the second one, right? So that's P of 1, right? Now P of 2 is going to be what? Let me go right manure. Control Alt T. Ha! P. Oh, let's do, wait. We are going to, let's do it the other way around. Hey, you thingy. How can I select? Yes.
So like if you were doing P of 8, and let's say, in theory, let's say that 5 wasn't there, so would P of 8 be 4?
P of 8 would be 4.
Okay,
Yes.
I get it.
Select all. Rectangular selection. And I can probably copy, and I can probably get something that looks like pages. And maybe I can figure out how to create a table. So we have this thingy, right? So now we are going to insert a table with headers. Oh, beautiful. So this is J, P of J, and then we're going to do OPT of J. So J is 1. What's P of J? 0, right?
And that's not including 1. So that particular.
Yes.
Yeah.
Yeah.
So does P? I could have sworn you said before that P of J can include the job, or it's OPT?
No. OPT is, but P is just what's the highest other jobs that you could include.
Okay, so P of J is telling you what is the most efficient way before we include this job.
Exactly.
And then OPTJ is like, all right, so what if we include this job? What do we see?
Exactly.
And then it'll pick between one or the other in
Yes.
determining which is.
So let's do 1, 2, 3, and 4, right? P of J for 1 is 0, for 2 is what? 0. For 3?
0.
For 4?
1.
1, right? Make sense?
Can you show J is the time?
It's not time. J is the number of job. Yes.
Can you show why 3, 0, and 2?
Okay. 3, right? For job number 3, you're comparing only with the jobs above it, right? Is there any job that doesn't overlap? No. So what's the highest number that doesn't overlap? 0, right? Because 1 is my first one. For 4, right, what happens? 1 doesn't overlap, so P of J is at least 1. 2 overlaps, right? So I'm doomed, right? That's all I can do, right? Actually, for 5, what's going to be P of 5? 0 again, right? Right? Can I get more? So 5, 6, 7, 8. Ah, fits perfectly. So P of 5 is what?
0.
How about P of 6?
No, 1 and
2. So 2.
Only
2 is the highest one.
Oh, so
right?
you just take the highest.
I just take the highest one.
Okay.
How about 7?
3.
3. And how about 8?
5.
5. Right? So when I calculate OPT, I look at, okay, there is 2 possibilities. Either I include the job or I don't, right? If I do include it, what's my value? It's going to be the weight plus however much I can do up to P of J, right? Because those are the ones that don't overlap. If I don't include J, then it is however I can do up to just 0 for not including J plus OPT of J minus 1, right? So in here, OPT of 1 is going to be 10, right? We said that each job has weight 10 times its thing. So OPT of 2, right, is either, if I include 2, what's the value? 20. If I don't include 2, what's the value? Actually, it is 0. Wait, no. If I don't include it, it's 10. You're right. Right? If I include it, it's 20 plus 0. If I don't include it, it is, right? OPT of J minus 1, which is OPT of 1, which is 10. Which one is better? 20, right? So I'll choose 20. Now, how about 30? It's either OPT of 20, right? OPT of 2, sorry, which is 20, or 30 plus OPT of 0. So it is 30, right? So up until 3, I have include 3. Now 4 becomes more interesting, right? It's either, if I include it, what's the value? 40 plus OPT of 1. So it's 50. Right? If I don't include it, what's the value? 30. Right? Which is OPT of 3. So for this, I'm doing 50. Right? For 5, I go back to 0, right?
Yeah.
So in here, I actually have a tie. Either including it or not including it, I get the same thing. I get 50. Does that make sense? For 6, I get either 50 or 80, right? 60 plus 20, which is OPT of 2, right? So I'll choose 80. For 7, I'm going to do either OPT of 3, which is 30 plus 70, so that would be 100, or 80. So I choose 100, right? And then for 8, I do either 100 or 80 plus OPT of 5, which is 130. So. Does that make sense? How long does this take me?
It's definitely shorter because you're saving, but
How short is it? for looking at every job, right? Once I have sorted and calculated P of j, right? How long did this process took me, the OPT part? It's order of n, right? It's linear, right? Does that make sense? Now, how long does sorting take? N log n, right? And then, how long does calculating P of j takes? The naive version, right, would take how long?
Is that n?
No, for every element, how can I know which one is the highest one that doesn't overlap? I need to go look at all of the previous ones, right?
Up to n squared.
So it's n squared. It's n squared ish over 2, right? Does that make sense? I could actually cheat and sort in a different array also by start time. Now sort by start time, right? And then do something like a binary search-ish by start time, right? To make it n log n. So the naive stuff would give me n squared because of calculating the P of j. There's slightly more advanced that will give me n log n, which is sorting anyway. So I converted it from exponential, 2 to the n, to n log n. Isn't that cool? If you think about just about this stuff with the pre-calculations, converted it from exponential to linear, which is amazing. Does that make sense? Yes? Some sense? What do you do if it doesn't make sense? Sorry? Study hard. Good. Do an example, right? Come up with your own numbers and do it, right? It's not that hard to, right? Does that idea make sense? Yeah, I'm looking at the wrong thing. This guy. So my OPT is going to be either 0 if j equals 0 or the max of the value of j plus OPT of P of j and OPT j minus 1. And at any given time, I'm just doing it. If I do it the other way around and memorize it, it just works. It is slightly more computational effort because I need a hash table or something like that to memorize, right? An array is the fastest and best hash table if you know exactly the number of things. You're just going to be searching by index. But it's not that terrible. And if I do it with memorization, I don't have to think. Yeah, this is yeah. If this is the brute forcing, right? I have compute opt of P of j, compute opt of j minus 1, and so given that these things overlap, right? I end up with it's not quite 2 to the n, but close. With memorization, I just memorize these things, right? and then I can do it with a table, right? How do I find the solution? I would actually not do this, but that's okay. Theoretically, right, you can just go back and figure out which number you used, right? I would normally, if I was implementing this, I would store whether I chose to include it or not, right? And then just go through it. But you can recalculate it. I hate comparing numbers. But that's just me. The bottom-up version is using a table for that stuff. Is this cool or what? Dynamic programming is really, really cool. Sorry?
Sorry, that was pretty slow.
Cool. Now, other examples, right? I'm hoping that you have all seen least squares minimization, right? Regression, linear regression in statistics. No? Are you serious? You never took a stats class?
I took stats, but we didn't do this.
You did. No?
Maybe in a different way than
Maybe.
it's presented here.
Oh, well, no. You just do this piece, right?
Yeah.
Linear regression is this, right? You have a bunch of points, and you're trying to find the line that minimizes the square of the errors, right? And why do we minimize the square of the errors? They used to, instead of the absolute value of the error, right? The mathematician in here, why do we do that now? They used to tell you, right, that it's like, oh, because you want to penalize bigger errors too, right? Rather than just, you can't do average because average would be 0. But average of absolute value, right? It really was because we couldn't do it with computers, right? We didn't have computers, and squares are derivable, and so they came up with a closed form derivation of the thing that minimizes. They use calculus to minimize, right, that error. And so yeah, you have a formula. Life is good. You need to be able to regurgitate that formula now. It's just, right? It's a standard formula in statistics. It's probably not a bad idea to have understood it at some point in time, but on the other hand, it's just a formula. You can apply it. You can build an algorithm for doing this, right? Now, and that has nothing to do with dynamic programming. It's just plain calculus. It's basic statistics. Now, there is this other cool idea of when you do linear regression, right? Let me deviate a little bit. When you do linear regression, it works really well if your data looks like a line, right? What do you do if your data doesn't look like a line?
Break it up into lines?
Well, this is what they are proposing. What you normally do is you transform your data, right? Maybe I apply logarithms, or maybe I square it, or maybe I do the square root of, right? Until I torture it until it looks like a line, do the regression, and then untorture it. Now, what they are proposing, and where we use dynamic programming, is, well, how about I think of it as a sequence of lines, right? And what would be the meaning of this? You have processes that are more or less linear, and then you have big changes, right? You have growth of something here, and then here you change your machinery. So your error rates become different, right? And here you changed again some configuration in your factory, right? Or you changed the law, and so the economy started growing more or less, or whatever. Does that make sense? Now, if you're gonna look at your data as my data may come like this, right? What can I do? Well, could try to, right, think of it as a bunch of lines, right? What if you cheat, right? Can you fit your data perfectly with lines? With zero error.
Just have every point line.
Yes, just make a line between every point, right? It's perfect, right? It fits perfectly. So we need some way of penalizing the number of lines, right? We want something with a good error that doesn't have too many lines, right? So that accuracy is the error and parsimony is the number of lines, right? And when you are doing this in real life, you decide how many, right, and what. But so what are we going to do? How can we decide, given, right, somebody gives me this. My optimization function is E, the sum of the sums of the squared errors in a segment, and a constant for the number of lines. In fact, it's, right, doesn't even need to be constant. Could be any other function, right? Maybe I do the square of the lines because I don't want too many lines, but a few is okay, or something like that, right? Some weighted average of those two things. Does this idea make sense? So at any given time, I'm gonna say, oh, let me calculate, right, these two values, right? What happens when I look at a point, right? What do I look at?
It's XY value?
Well, but here, when I'm going to consider the point, what am I going to consider, right? What I really need to consider is I'm going to make a line with these guys, right, up until some point, and then I'm going to break, right? Then from here on, right, imagine that I'm going to line these three last points, right? And then from here on, from the fourth point from the back on, I don't need to recalculate. I just say, well, that's it, right? Whatever was the optimal value at that time. Does that make sense? How do I know how many points do I want? I don't, so I have to calculate all of these guys, right? For adding a point, I need to calculate how would it look like if I extend the segment all the way, right, for every other point. Does that make sense? So I have a multi-way choice. It's not just one, it's all of them. So, Oct4 is the minimum cost for points P1 to Pj. Eij is the minimum sum of squares for points P1 to Pj. To compute OPT of j, the last segment uses Pi through Pj for some I, but I don't know what's the I, right? And so the cost is going to be Eij plus C plus OPT of I minus 1. And I can't calculate Eij, right? This is just my formula for least squares, right? Because they're just one segment. And so my OPT of j is now 0 if j is 0, and if not, the minimum I need to calculate for every other point, right? For j between 1 and for I between 1 and j of Eij plus C plus OPT of I minus 1, which is doing a segment, right, with the last point and every other possible point.
So I just wanted to kind of visualize this. So if you're working on those first 3 points, I guess the first thing it would do is it would just kind of automatically make a line from the first to the second because there's nothing else happening
Yes.
before it. And then on the third one, it would check, okay, so if we make a line segment straight to the third one, you know, what's our errors and everything? And what's
From the
errors?
third one to the second, right? Can I make
Yeah.
2 line segments, one from the first to the second and one to the second to the third?
And is it, which one is minimizing that E plus something?
That's what you calculate.
Yeah.
Yes.
And then going on, we check whatever was optimal for that one.
But I need to check over every possibility for 4, right?
Yeah.
I need to check, well, do I make a segment just between 4 and 3 and leave, right, 1 and 2 alone, right? Or do I make a segment 4, 3, 2,
Okay.
right?
Yeah. Okay. So it's even our most efficient solution is much more involved than the last problem we did.
Yes.
Okay.
Now you're going to try all of the possibilities instead of just one.
Okay.
So now your table is going to slightly suck. I mean, we need to calculate this, right? And then here we need another for loop. So this, instead of being, right, once I've calculated this stuff, right, it takes me quadratic, right? I need a nested for loop, so it's quadratic-ish. Does that make sense? Well, depends on how long does it take me to calculate this, right? If they were all calculated, right?
Those errors have to be calculated on the fly, depending on your.
You can actually cheat. You could calculate them on the fly, and that would make it order of n cubed,
Yeah.
right? But you can actually cheat and reuse the previous ones. If you look at this formula, I'm adding up all the y's and I'm adding all of the x's. So in order to calculate the next one, I can reuse
Okay.
some of the previous values, right? So you can
Okay.
shave off an order of n, so you can make it
Just n squared.
n squared, yeah. By, right, in one pass you calculate all of the i's, right? Or, yeah, all of the j's for one I or something like that. And then the actual dynamic programming part is n squared. Isn't this cool? It is, right? It is actually really cool. Now we are going to see one more. We are going to start talking about knapsack. Actually, I'm surprised that they didn't put it in the greedy, because it's also one of the examples of greedy algorithms. The knapsack problem is actually similar to some of the scheduling things, but they put it as you find gold or gems or something, right? You find treasure, you have to put stuff in your knapsack. There is a weight limit to how much you can carry. What do you put in, right? The greedy algorithm is the fractional knapsack. If you have just gold powder and silver powder and copper powder, right? What would you do?
Fill out the brim.
Take out all the gold, right, and however much of the silver I can make, right? And that will be optimal. Now, imagine that you don't have powder, but you have ingots, right? And they weigh differently, right? So taking this item takes up this much weight and give me this much value. Which one do I take it, or do I leave it out and take some other stuff that may give me more value for the same weight? And at some point in time, I'm wasting some extra weight because maybe there is nothing that weighs less than what I have right now. Does that idea make sense? So you're filling your knapsack up until a weight limit, up to a weight limit, maximizing the value. With non-fractional, with integer knapsack, greedy doesn't work. It's not terrible, it just doesn't work. And you can come up with arbitrarily sucky problems that will make it arbitrarily sucky, right? Basically, you could say, get the one with the maximum value, right? Or add the ones with lowest weight, or add the maximum ratio of value to weight. But since you're going to waste some at the end, that still doesn't get you optimal stuff. Adding the maximum ratio may fill up 51% of your knapsack, and now you don't have anything else, right? That kind of stuff. How can we do dynamic programming, right? I could say, okay, let's do subsets, right? If I'm brute forcing, that's what I'm doing, right? 2 to the n is every possible subset, right? However, when I try to do it as dynamic programming, it's like, okay, what does it mean that I selected this guy? Doesn't necessarily mean that I may not select any of the other guys. What does it mean? I now have less weight available, right? So what I need to do is add more subproblems. Add weight limit. So my table is gonna be on subset of items I through j and weight limit. Does that make sense? So I'm adding one more variable, which is the weight limit. If I select the item, right, what's the value that I'm going to get? The value of the item plus the value of at any given weight, right, at the maximum weight, the value of the item plus the value of 1 minus and taking out all the weight that I took. Does that make sense? If the weight was 5, I'll do I up to I minus 1, but now my weight is 5 minus. So I just go and look that up in the table. If I don't select it, then it's just open the previous one and this weight.
So it seems like these last two examples of dynamic programming, they seem like almost like a workaround brute force. It's like you're brute forcing it, but saving what you've already brute forced, so you don't have to brute force.
Yes,
as hard of a
exactly.
way.
That is what dynamic programming is.
Okay.
As long as you put your brute forcing in terms of overlapping subproblems. So you need to think about how to brute force it as overlapping subproblems and then save time.
Okay.
Does recursive backtracking count as dynamic programming?
Not necessarily, although they may put it like that. No. Now, in this case, right, for this thing, should you memoize or should you build your table? What's the problem with building your table? You may not need all the things in the middle. Right? If I build my table, how long does it take? It takes I times W, the weight limit. It's a different, it's not size anymore. It's not the number of items I have, but my weight limit, right? Imagine that all my weights are multiples of 5, right? If I calculate this stuff, then I will never need to calculate 0, 1, 2, or 1, 2, 3, and 4, right? I would only need to calculate 0, 5, 10, 15, because all my weights are multiples of 5.
In memoizing, would you start at the highest weighted object?
Yes,
or-
you start here. You start here, right?
Mm-hmm.
And in order to do this, you call these two guys, right? And they keep going down.
So it brute forces kind of in the opposite direction, so that when you brute force the highest weighted one, you got to brute force almost everything below it. And you've already
Maybe
brute forced
you
it.
gotta brute force whatever you gotta brute force below it. Maybe it's everything, maybe it's not. Maybe all my weights are beautiful and I only have 5 items, so I ended up only doing 10 things on the table.
Okay. I guess what I'm missing is how we would be skipping elements by memoizing that we would not be skipping by building a table.
Maybe if you are here, right?
Mhm.
If the weight is 40, you may never use, say if your weight is 3 for
Yeah.
this guy, you may never use this, and this,
Mhm.
right? You never use this weight,
Mhm.
these weights, right?
Okay.
And so if you memorize, you don't have to calculate them. Which one is better? Yeah, it depends. Right? But in this case, I would probably use memorization because there is probably tons of holes. Does it change the order of the algorithm? No. Still order of I times n. Is this better than 2 to the I? Sorry, I times w. Is it better than 2 to the I?
Depends on W.
Depends on w, right? Depends on w with respect to I.
Mhm.
So, maybe. In fact, this is called pseudo-polynomial time. It's polynomial, but with an extra thing, right? So it depends on. In a way, this is the same kind of cheating thing that sorting, bucket sorting does. Like, oh, as long as, right? So it's the same kind of cheating. We will see later the decision version of the NACSA problem is actually NP-complete, so there's a slightly different version. We'll see NP-complete is where we think we are doomed. Things that have to basically, things where you have to brute force, right? And so what we'll show is that this, you have to brute force it. Or we think you have to brute force. It's actually an open question whether P equals NP. And we'll see what does that mean. By the way, you will also see P and NP and those guys in theory of computation. In theory of comp, you actually formalize what the heck is an algorithm and then go spend a semester talking about P and NP. In this, we hand wave number of steps and things like that. Over there, you explicitly define what's a step and then go counting, doing things like that. And we'll see, right, a lot of times these well-known problems also become kind of like standard solutions. So people will just go and transform the problem. It's like, oh, I'm giving this optimization problem for airports. It's like, oh yeah, it's just a knapsack, right? So I will figure out how to solve the knapsack. So they study that stuff. There is a polynomial time algorithm that's not optimal, but is within 1% of optimal, which is pretty cool. We have 5 or 7 whole minutes. 9 whole minutes. So we can finish this other guy. Did I just kill it? No, perfect. And this is just another cool example. This is arguably the coolest area of computer science-ish. I love computer science. I would probably be a programmer if I was 18 again. I would probably do the same thing over again. The only thing that could get me to do it is do it in biology, right? And that's really because DNA and those kinds of things are now done with computers. DNA is the basics of genetics, right? Is how we encode genetic information, sort of, kinda. We have 4 bases, basically 4 kinds of molecules that repeat. And RNA is similar, but it has some of the same and 2 different. One different?
Instead of T, it's U.
Instead of T is U, okay. And RNA is used to share that genetic information and transmit it.
Yeah, it copies off of DNA to make proteins.
One important thing, DNA is double-stranded, right? So those proteins are matched with their opposite all throughout in a really weird 3D form. RNA is single-stranded. So it tends to actually fold onto itself instead of being a strand. So the secondary structure of RNA is this folding. And I don't know exactly why, but it's important. Biologists know why. Bases are the letters, and base pairs are the bases that are paired. Only certain ones can pair with each other. The secondary structure of RNA tends to be a set of pairs, right? The things that you're matching, the numbers that you're matching, that satisfy 3 things. Watson-Crick, so they're actually complementing. A matches with U, U with A, C with G, and G with C. No sharp turns. The molecules kind of don't like to do sharp turns, so you have at least 4 intervening bases in between. So the difference between I and J is at least 4. And non-crossing. And they actually fold to minimize free energy, or they tend to fold to minimize free energy. But that, in terms of strings, tends to be the number of base pairs. It's not quite, but it gives you a really good idea. So if the bases are paired, they won't interact with each other, right? They won't interact with other stuff. That's what you want, because if you can interact with other stuff, then you can mess up your information. So the goal for the dynamic programming algorithm is, given this RNA molecule, which is a string of characters, find a secondary structure S that maximizes the number of base pairs. If you think of them as 3D-ish or 2D-ish, this is what they look like. If you think of them as a string and just pairings, right? This is what it looks like, and it's probably a more useful for us visualization. A sharp turn is when you have only 3 bases in between, and a crossing is where the i's and j's of 2 pairs cross, right? And those are not allowed because they would break, they would not form this kind of structure. So what can we do? Well, what I'm trying to find is the maximum number of base pairs in a secondary structure of a substring, right? I can say, okay, I'm going to try all of the possibilities, right? So match bases BT and BN, where N is the last one. I don't get the right shape of the problem, right? So the way that we can cheat is use intervals, and so have the substring also, right, start at a different place.
Wait, what? Like, you're solving it by splitting it into sections of the RNA?
If I go to, if I'm going to join base 25 with base 15, what I'm going to do is say, okay, I'm going to join 25 and 15, and then I'm going to check how much is from 1 to 14, and then from 15 and 25.
Okay.
So I need to calculate intervals rather than just from the beginning to here.
Is it that particular property that results in the kind of circular without branching trees that we saw in that first example? Not really?
No.
Okay.
And a cool thing about this is that you have to solve it in the shape of the interval if you're not doing memoization, right? So you would solve it in diagonal. You sort it by length of interval, so you have to solve it diagonally, or just memorize. Isn't this cool? Quick review. Sorry, I'm taking a minute or two of your life. We end up with a polynomial number of subproblems. The solution to the original problem can be computed from subproblems, and we have a natural ordering of subproblems from smallest to largest, so that we can compute our table. We saw 4 ways, or 4 examples, right? Binary choice, I either include this guy or not. Multi-way choice. Adding a new variable that's completely different in knapsack. and intervals for RNA. Top down versus bottom up, it probably depends on the problem and depends on what makes sense to you. I like recursion. I normally, in many ways, I would normally do memoization just because it's easier, although for the well-known things where you have an array, it's much more efficient to do it with the array. And we'll talk next class about more of this stuff.